Are there questions? Okay, so if there are no questions, I'll begin. So last time we learned that the gravity is described by curved space-time, right? That the effect of gravity, according to general theory of relativity, the effect of gravitational field is simply that the space-time is curved. And we tested it, okay, at least in some limit, it reproduces the Newton's laws of gravity, Newton's equations of motion. Okay. So today we will try to work out some consequences, okay, and also some general principles. Okay. So let's suppose that we have a space-time point. Okay, let's suppose that we have a trajectory. Okay. So this is a trajectory in space-time. Okay, and you have learned that in the absence of any other force, any force other than gravity, okay, it satisfies the geodesic equation. Okay. Now let's suppose that we have some point x naught. Okay, let us put a 0 in the bracket so as not to confuse with the index. Okay, some arbitrary point on the trajectory. Okay. Then from what we have learned so far about Riemannian geometry, we know that it is possible to find a coordinate system x prime. Okay. So that in that coordinate system, at x naught, g prime mu nu becomes eta mu nu and gamma vanishes. Okay. So it is possible, given x naught, we can find a coordinate system in which so in this coordinate system, the equation of motion looks like at x prime equal to x prime naught. So this coordinate system is what we call local inertial frame. This coordinate system and what we see that in the locally inertial frame, the equations of motion look like the equation of motion in flat space-time, in absence of gravity. Right? So this looks like equation of motion in absence of gravity. Because if there is no gravity, the metric is eta mu nu and the equation of motion will be like this. Except that here we cannot make the equation of motion look like this in the same coordinate system everywhere. Okay. At every space-time point, you have to change your coordinate system, and in that coordinate system, the equation of motion looks like that of a free particle. Okay. So this is lifted to a general principle, which is called the principle of equivalence. which says that given any space-time point, it is possible to choose a coordinate system. Let's call it space-time point x naught. Which is this clear? Okay, that given any space-time point, we can choose a coordinate system, which is what we'll call local inertial frame, so that the equations of motion looks like that in absence of gravity. Okay. So we are going to make use of this. Okay. But before we make use of this, okay, let me just mention one thing, which is that this is not a sacred principle. Okay. Unlike the invariance under coordinate transforms, okay, that's a sacred principle, because if you give that up, right, then the theory has to be changed altogether. Okay, because change of coordinates shouldn't affect the that you should be able to describe a system in any coordinate system, right? And the form of the equations that you have shouldn't depend on the choice of coordinates. That's a sacred principle. Okay. But this is not. Okay, and this is not a sacred principle, because it is possible to change your equation of motion, okay, in such a way that you don't violate general coordinate invariance, and nevertheless you violate principle of equivalence. Okay. So let me just give an example. Okay, we can cook up many examples. Okay. Let's imagine that the equation of motion was not this, okay, but something like this. This is ordinary derivative, because it doesn't really make a difference. Imagine that you had a term like this on the right hand side of the equation of motion in the presence of gravity. Yes.
This principle equivalence is saying that in any time, by doing some manipulation, you can as the laws of physics will be anywhere else will be there.
Exactly. That it will be as it was in the absence of gravity.
Stating the relativity in the sense that laws of
yeah, that is true. But here it's saying a little more, right? Because that the generalization of that will be general coordinate transformation, right? That if you make arbitrary change of coordinates, laws of physics should remain the same, right? But principle of equivalence is something saying something more, that making change of coordinates, you should be able to erase the effect of gravity altogether. Okay? So this equation, for example, will be consistent with general coordinate invariance, right? You can easily verify that if you change x to x prime, okay, you have to look at the transformation of this, you have to look at transformation of this, okay? But this equation will be invariant under such transformations. Okay, because I have taken appropriate tensor combination on the right hand side. But this will not satisfy principle of equivalence. Because let's imagine that now we go to local inertial frame, okay, in which we can erase the effect of gamma. Okay. So what will the equation look like, right? So in local inertial frame, to x prime mu, this will be eta mu nu. Right? This is not what you had in absence of gravity. Right? Because gravity introduced this, right? This was not there in absence of gravity, right? So this is an example where the equation doesn't satisfy principle of equivalence. Okay. And in the full theory of full quantum theory, we do expect such terms. Okay, so in that sense, principle of equivalence is not a sacred principle, because you do expect that when you include all effects, right, including quantum effects of gravity, there will be such terms generated. Okay. And in fact, there can be it could multiply by some arbitrary constant. Okay, this is just one example. There are many such examples you can write down. Okay, and it could even depend on the type of particle. Could depend on particle that you consider. So if you are studying the motion of the electron, it may have one constant value, right? If you are studying the motion of the neutrino, it may have another constant value, and so on. Yes. No, geodesic equation is not corrected. It's simply the particle doesn't travel along the geodesic. Right? Geodesic equation is this is equal to 0. But violation of principle of equivalence tells us that the particle doesn't travel along the geodesic. There is an extra force due to gravity, right? Which is this. Gravity is not uniform everywhere. Yes, but even if gravity varies, right? This is also valid when gravity varies, right? But if this side was not there, right? This obeys principle of equivalence, because this is saying that in the local inertial frame, the effect of gravity is erased. Right? That statement is essentially for free particle or particle which is only subject to gravitational force. That statement is the same as saying that the particle travels along a geodesic. This is 0. No, GR doesn't have that term. GR by construction, right, doesn't have that term. Exactly. We do expect such terms to be there. I mean, it will be very surprising if such terms are not there. You can think of it that way, or you can say that the gravity has additional effect rather than just making that particle travel along a geodesic. Right?
So then when are we sure that
yeah, we are never sure, except that you can estimate what these constants will be, right? And this constant is very, very small. I mean, whatever other effects you get, right? Other quantum effects, or sometimes even in string theory at classical level, you get such terms, but those constants are extremely small. So that's why you don't have to worry. Because R is the effect of gravity, right? Yeah, exactly. In the absence of gravity, R would have been 0. Right? In the presence of gravity, R is there. Right? Principle of equivalence tells us that those invariants don't appear in the equation of motion. Yes, eta is a diagonal matrix, because in the local inertial frame, in the prime frame, the G mu nu is eta mu nu. Right? That's why eta has become the diagonal. Yes. Why is R not 0? Because R requires calculated in the second derivative, one more derivative, right? Gamma you can set equal to 0, but R you cannot set equal to 0. Right? It may happen that for some background R may be 0, right? but not in general.
Geodesic equation. I mean, the very first day we did not talk about any. Everything is mathematics. The only extra term that we introduced was metric.
Yes.
Till we get the geodesic equation.
Yes.
Where can I see the gravity?
So the principle of equivalence tells us that the effect of gravity is captured fully by saying that a particle travels along a geodesic. Right? That is the statement. This is a geodesic equation, right? So principle of equivalence is the same, is equivalent to saying, at least for particle without other forces, that particle travels along a geodesic. Yes. Oh, the metric is the effect of gravitational field. We identify the G00 component of the matrix that you can only get by comparing with the Newton's equation, right? Okay. So metric, I mean, it's a question of, I mean, if you have gravitational potential, right? How do you get the gravitational potential? By experiment, or Newton's theory tells us that given a mass distribution, how to calculate gravitational potential, right? We'll see a similar feature for the metric, that given a mass distribution, how to calculate the metric, right? That will be one part of the course. But right now we are saying that suppose somebody has given you the metric, which captures some gravitational field produced by something, right? Then given that, how does a particle feel that? Right? That's this equation. See, Newton's law of gravity can also be divided into two parts, right? One is the gravitational potential that is produced by a particle, right? The other one is that given the potential, how does another particle move in that, right? So what we are doing here is to answer the second part of the question, right? That given a potential, right, or in this case, this says that they have to specify the metric, how does a particle move in that background, right? And there, the principle of equivalence tells us that a particle moves along a geodesic, right? But that's not a sacred principle. It can be violated without violating the invariance and the coordinate transformation, right? And here I just gave an example that this satisfies is invariant on a coordinate transformation. Nevertheless, it doesn't satisfy principle of equivalence because the particle is not traveling along a geodesic, right? There's something on the right hand side. Yes.
In literature, it is sometimes mentioned as there are two equivalence principles. One is the weak one, the other is the strong one. Is there any major difference? And if so, let's say, can there be any theory which violates one of them and not the other?
Okay, I now don't remember exact distinction between weak and strong. I mean, so what is the difference? Can you remind me? Yeah, okay. I mean, I'm going to use principle of equivalence in this way, and I'll also say another, I mean, a generalization of this, right? Maybe then that I don't remember now what is strong, what is weak, right? But this is the sense I'm going to use it. With equivalence. So equivalence principle by definition is a geodesic equation, that particle travels along the geodesic, because anything extra that you get, right, has to be constructed out of tensors, right? And the tensors can be non-vanishing, right? It may happen that for some particular metric background R may be 0, right? In which case this term doesn't arise. But if you say that for any metric, right, the principle of equivalence is valid, that means by in local inertial frame you should be able to erase the effect of the metric, then geodesic equation is only one.
Suppose we have something like G mu nu dx mu d. That is not the geodesic equation, but it's compatible with principle of on the right hand side.
Yes. Well, you are saying why didn't I write something like that?
I mean, so it's not really equivalent, right? The geodesic equation can add some term to the right hand side also.
But that will not vanish when in a local inertial frame.
Suppose G mu nu dx mu du.
Yeah, so that will remain, right?
So G mu nu is 0.
Oh, it's theta mu nu, right? It's not 0. I mean, the one if you can things which you can set equal to 0 cannot be tensors, right? That we have learned, right? Because if you can set it to 0, it is 0 in all frames. So anything that you can set it to 0 is not a tensor, right? And here you already have made sure that it's invariant a general coordinate transformation. So anything else that you can add must be constructed out of tensors. Yeah, so just dx, that's why I have written this way, right? Single dx to du will not work because u goes to u plus u goes to lambda u should be a symmetry, right? So it should at least have two factors of dx du, but you can certainly write many other things with this property, right? These are in no way the unique result. Okay, I just gave it as an example that it is possible to violate principle of equivalence and yet be consistent with general coordinate variance.
Similar equivalence begins from the effect of gravity in a local unit.
Yes.
But not necessarily, I mean, it's not, that is a weaker condition than general coordinate.
Exactly. That's right. Okay. Now we are going to assume principle of equivalence is valid. Okay, and we will assume that it is valid in a much stronger sense that I have described so far. Okay, and that sense is the following: that let's suppose that we know the effect of some forces in flat space-time, electromagnetic force, for example. Okay, we know how a particle moves in flat space-time under the effect of electromagnetic force. Okay, and that's captured by essentially by Maxwell's equation with sources and Lorentz force law. Right? That tells us how electromagnetic field affects a charged particle, and the Maxwell's equation tells us how a charged particle produces electromagnetic field. So principle of equivalence applied to this system will tell us that in the local inertial frame, okay, where you can set gamma prime equal to 0, the equations of motion will be identical to the equations in absence of gravity, namely Maxwell's equation and Lorentz force law will hold exactly as it holds in absence of gravity in the local inertial frame. Okay. So all laws of physics that you are familiar with in the absence of gravity can be generalized to what happens in presence of gravity by simply demanding that in the local inertial frame the laws should remain the same. Okay. And the point is, once you know how it looks in the local inertial frame, okay, you can transform it back into arbitrary coordinate system, right? But because that's a change of coordinates, right? You are not changing any equation. Okay. So this principle can then tell us whatever happens in presence of gravity, how all the laws that we are familiar with change in the presence of gravity. And we will see examples. So we'll work out in detail the effect of electromagnetism and electromagnetism, okay, in presence of gravity. Right? How do the Maxwell's equation and the Lorentz force law get modified in presence of gravity by following exactly this principle? Is it clear? Okay. So now we are going to describe a practical application of whatever you have learned so far. Yes.
So, you say that this kind of terms can appear with the constraint of
Yes. But the effects are very, very small. Yes, yes, indeed. It's something similar, exactly. Exactly. Yeah. It's exactly something similar, right? I mean, if you want to write in terms of Feynman diagram, right? Imagine that you have the electron and the neutrino. Okay. So both coupled to gravity, okay, by this universal principle, by gamma. Okay. But once you take into account quantum effects, right? The electron, this has an extra term, for example, where this is a photon, this is graviton, and this is a quantum graviton. So this will give some effective new kind of interaction between the electron and the graviton that is mediated due to the photon. Okay. This one doesn't have such terms because neutrino doesn't couple to photons. It's neutral, right? So these diagrams differ. Okay, and that's the way you will see that the extra quantum effects could change the effective interaction of a particle with background gravity. Yes, so the last, if you remember in the quantum field theory, right, we did quantum calculation But then we said, okay, that can be rewritten in terms of an effective action, right? From where you can derive classical equations. The same thing you can do here, right? You can do quantum calculation, but at the end you can recast in the form of a force, effective force, right, that acts in the classical system. Yeah, you can do it. I mean, you have to find a quantum theory of gravity, right, where all the infinities are under control. So in string theory, for example, you can do such calculations and check that there is a extra force, right, which is not universal.
Experimentally can we characterize the kind of term we can expect on the right hand side? They are supposed to be fine parameter reparameterization invariant, general coded invariant, and consistent with the tensor notation. Has any kind of
No, experimentally, certainly there is no detection of any kind. No violation of principle of equivalence has been detected, and you don't expect. If we do detect, right, with the current experiment, then there is some problem, because that will basically change our understanding of general relativity, right? Because as I said, if these kinds of corrections, right, do come in quantum theory, but their effect is so small that we don't expect them to be visible into this experiment.
What kind of experiment do we get such?
Well, if you could study the motion of the electron and neutrino in gravitational field and compare them to very, very high accuracy, you will see that electron and neutrinos move differently in gravitational field. I'm just cooking up something, right? I mean, it's that may not be the most efficient way to try to detect such things.
Compare what?
Trajectories, right? Take a gravitational field, compare the trajectory of an electron to the trajectory of a neutrino, right? The trajectory of an electron and trajectory of a neutrino. Okay, maybe for that this is not. Well, okay, yeah, this is good enough. I mean, if you have a complicated background, right, where R is non-zero, then the electron and neutrino will see the difference. Yes, indeed, it can happen. Okay, for massless particles, right, these modifications are more controlled, more under control. Yeah, so you have to look at the massive particle propagation. Okay, because massless particles have an additional constraint, right? The null trajectory, right? So that's why the massless particles are more complicated.
So that's not violated.
No, null trajectory by definition, massless particle has to propagate a null trajectory. That you cannot violate. Okay, so now let's try to think of an experiment. So let me describe the steps. So first, we construct two identical clocks. Okay, and let's just to make things completely definite, let's suppose that we manufacture the clocks in a factory in space-time without gravitational field. Okay, this is not really necessary as long as they are constructed under the same environment, but let's suppose that we have constructed them without gravitational field in some space-time. Okay, go out in space and construct them. And the clock is such, the clocks are such that every second, the second hand moves one step. Okay, so it just jumps. Okay, it's not continuous motion, it just jumps every second from one position to next position. Okay, so that's the clock we construct, 2 clocks. The second step is to consider a static gravitational field. Okay. So notice that G mu nu can depend on the spatial position but not on time. Right? That's what we mean by static gravitational field. It doesn't depend on x naught. So this description is not a coordinate invariant description, right? But that's okay. We just see that. Let's suppose that there is some choice of coordinates in which G mu nu depends only on the space coordinates and not on the time coordinate. And then place one of the clocks at x1 and the other at x2 with its observer. With an observer. Okay, x1 doesn't have to have an observer, but in x2 we'll have to have an observer who can see things. Pardon? That it's independent of x naught. Yeah, some coordinate system in which G mu nu doesn't depend on x naught. Is this clear? That's the meaning of static. That it's like, okay, let's imagine that the Earth is static and the gravitational field of the Earth will be one example, right? Which is not changing with time. Yes, yes. There is no condition on that so far. Is that clear? So there is a preferred coordinate system in which it depends only on the space coordinates. And of course, if you make a change of coordinates, it will change, right? And it will start depending on all coordinates. So static means there is a preferred coordinate system in which all components of G mu nu depend only on the vector x, right? The d-1 space components, but not on the time. Okay, and as an example of this will be Earth's gravitational field. Right? Earth, of course, is moving, so it's not totally static, right? But let's imagine that Earth is static. Then its gravitational field would have this property. Is clear? So now the third step is that the observer at x2 watches the movement of the second hand of the clock at x1 and finds the interval between two successive movements using the clock at x2. Okay, so the clock is at x1, right? The observer is sitting far away at x2 and watching that clock. Okay, that clock second hand moves in steps, right? Every second it moves one step. So this observer watches that second hand moving and tries to find the difference between the two successive movements. But of course, to see the difference in time, the observer needs a clock, right? And it uses the clock that is there at x2. Is it clear? The question is, what will be the interval? What will be the result? So from usual experience, we would think it's 1 second, right? That clock is moving every second. So the observer somewhere else will see the clock move every second. Okay, but we will now try to answer this question using what we have learned. Is it clear? So let's suppose the clock at x1, second hand of the clock, moves at x0 and x0 plus delta x0. Okay. So the first task will be to find what is delta x0. Okay. Is delta x0 1 second or is it something else? Now the reason that it may not be 1 second is because there is a gravitational field present, right? And we don't know how gravitational field will affect the movement of the clock. We can figure this out using this formula for ds squared, okay, which is g mu nu, in this case x, and this is also minus d tau square, right? In terms of the proper time, this is minus d tau square. And since the clock is a heavy object, right, it moves along some time like curve, right? So the delta tau between these two successive intervals will be given, delta tau square will be given by minus g00 of x1 delta x0 square. Why? Because here, of course, you have to take dx mu dx nu, okay? But the only thing that is changing, the clock is sitting at x1, right? If it doesn't want to sit there at x1, we will just hold this. Okay, so it's sitting there, okay? And now the only x0 is changing. Yes, there is a proper time for the observer. Well, there are observed for the clock. The proper time for the clock. Okay, so this is the proper time for the clock. The other question is, what will be delta tau? Shouldn't that be plus? Because G00 is negative. Right? You remember we had taken the signature to minus 1, 1, 1, 1, right? Yes, so delta tau square will be minus of this. So it is eventually it is plus. Yes, of course, because G00 is negative,
Okay.
right? So it will become, otherwise it doesn't make sense, right? Then delta tau s better be real. Now, if you go to the local inertial frame, okay, we have to figure out what delta tau is, right? Whether we can say anything about the delta tau. So in the local inertial frame, right, the physics should be as if gravity was not there, right? Just normal special relativity should hold. And we have made the clock in such a way that in absence of gravity, right, we made the clock in a factory where there was no gravity present, right? In the absence of gravity, the proper time of the clock should record 1 second, right? Should move every second, it should move. Okay? And now if we apply principle of equivalence, okay, namely all laws of motion look like as if they are in the absence of gravity, right? Then whatever laws of motion are responsible for the movement of the second hand, right? It could be a mechanical motion, or it could be even atomic clock, right, or quartz clock. As long as the laws of motion look as if though no gravity is present, okay, and since the clock was made in the absence of gravity, we know that this should give you 1 second. Delta tau should be 1 second. Is that clear? So this is why we are using principle of equivalence, right? That it is that in presence of gravity, right, delta tau should still be 1 second, because gravity in the local inertial frame cannot change laws of physics. Okay, so exactly the same laws, right? If you use atomic clock, for example, right, the period of oscillation will be whatever it was in the absence of gravity, right? So if you have calibrated the clock in absence of gravity, that's what you should use. X1. Yeah, we are not using X1 anywhere. I'm saying take this, right? And now if you had gone to a local inertial frame, right? Suppose you had gone to a local inertial frame, delta tau is invariant under change of coordinates. So delta tau will remain the same. And in that frame, it's as if gravity is not there, right? So delta tau will be 1 second. Is that clear? So this tells us what delta x naught should be. So delta x naught should be 1 second divided by square root of minus G00 of x1. Since delta tau is 1 second. This is by principle of equivalence, right? So remember that we are using this because if there is a large term like what we wrote down there, right, like this, suppose C was large, right, then the presence of gravity could have changed the time period, right? We are assuming that that doesn't happen. No, you can equate proper times, except that the proper time between two successive movement of the clock may change, right? Because if gravity has additional effect, right, maybe it's slowing down the atom. Exactly. The 1 second will not remain 1 second, right? Suppose the gravitational force, the effect of these terms are so large, right, that whatever motion was executed earlier, right, in 1 second, now it will take 2 seconds. The second hand, suppose it moves in 2 seconds, right? Yeah. So there is a problem in the events, right? I'm just saying the dynamics of the clock may change. There are two successive movements of the clock hand, right? It's not a change of frame, right? You're right, a change of frame is change of frame, right? That is not going to change. But if the gravitational is, imagine that you have a clock, right, and you break it, second hand will not move, right? So external force can change the movement of the clock, right? So suppose gravity is such that it just holds back the movement of the clock, right? It slows it down. Principle of equivalence is a statement that doesn't happen.
So you're saying,
Right? We are of course assuming here that clock is robust enough so that external forces other than gravity, right, its resistance against external forces other than gravity, right? Otherwise you can worry that, I mean, if you have kept the clock at x1, right, sitting at x1 may not be geodesic, right? Clock may want to move somewhere, so we are putting some external force other than gravitational external force to hold the clock there. That shouldn't change the period, right? We are assuming that we have our space factor is robust enough that such external forces are not affecting the movement of the clock, right? But gravity we don't know, right? If principle of equivalence is violated, then gravity could. Okay, and we are assuming that principle of equivalence is valid so that gravity doesn't change the movement of the clock. Is that clear? Right, so that's where we are using principle of equivalence. So the laws of motion, the laws of anything, right, are unchanged in the presence of gravity if we go to local inertia.
Are not valid, it will actually change what we are mentioning, but then it is valid relatively rather than actually.
Exactly, that's right. When principle of equivalence is valid, right, then in appropriate coordinate system, nothing is changing, right, in the local inertial frame. Whereas if principle of equivalence was not valid, then even in local inertial frame, right, it could actually change that period because gravity may simply slow it down.
These kind of tests are like tests of principle of equivalence rather than test of GR.
Well, principle of equivalence is part of GR. Right.
There are other theories which still
General coordinate invariant, right? That could violate this. Yes, imagine that there are other theories of gravity, right, which has the same Riemannian geometry structure, but where principle of equivalence is not valid, right? And if the violation is strong enough, right, it could affect this result. Okay, so now this is not good enough. We have determined delta x naught. Yes. If principle of equivalence is valid. See, suppose you have calculated delta tau, right? Okay. Now you put a strong electromagnetic field, right? Magnetic field which pins the second hand. Suppose the second hand is made of some ferromagnetic material and you put a magnetic field which pins it, right? Then obviously it is not going to give the same delta tau, right? So if gravity had an effect like that, right, then it will not give delta tau, right? I mean, it will not give delta tau equal to 1 second, right? So that is the point, that we are assuming that gravity doesn't have that such effects, right? So there are two things. We are assuming that gravity doesn't have such effects, right? Another thing is that if there are any other effects, right, like magnetic field, etc., right, we are assuming that the clock is robust enough so that it can withstand any such extra force, right, non-gravitational force that we need to hold the clock in its place. Is that clear? Okay, so now we have to go to the next step. The delta x naught then is the change in the coordinate x naught between two ticks of the clock. Now you have to see what is measured at position 2. Okay. So the first thing you have to understand is this delta x naught, what change in x naught coordinate it translates to at position 2. Okay, so let me say here. So this is 1, this is 2. Okay, these are on the space. Okay. You emit at x naught here. Okay. It reaches at 2 at some time y naught, right? Suppose you emit at x naught and it reaches, sorry, this is x naught, sorry, x, this is up, x upward naught, and reaches at y naught. Okay. Then you emit one more signal between x naught plus delta x naught, and it reaches here at y naught plus delta y naught. You have to find delta y naught in terms of delta x naught. Some coordinate here is a metric static. This is not anybody's coordinate. This is not a proper coordinate for time of anybody, right? This can, ultimately you have to convert it to proper time of 2. But right now we are just saying, and how much is that in okay, any event in space time will have a space coordinate and time coordinate, right? So the first event is when a null geodesic, suppose you are sending the signal by a light ray, right? You are watching it, so light is coming along a null geodesic. So the first event is at x naught, the clock moves. Then the light travels along a null geodesic and reaches the point 2 at some time x naught. That's the second event, right? So second event has time coordinate y naught and space coordinate x2. Then the third event is from the position 1, okay, the next time the second hand moves, x naught plus delta x naught, okay, space coordinate is x1. Next event is that signal again travels along a geodesic, null geodesic to reach 2. Okay. The space coordinate by definition is x2. Time coordinate we don't know, we are calling it y naught plus delta. Is this clear? So you have to find out delta y naught in terms of delta x naught. Yeah, in principle, if you know the full geometry, of course, you can also find y naught in terms of x naught, but that will not be necessary. Well, you can put an observer at x naught at x1 if you want, right? But that observer has to communicate that information to 2, right? The observer at x1, right? So suppose the observer has another clock with respect to which he or she is measuring time. Then obviously it will be 1 second because that clock will move in the same way, right? Two identical clocks at the same point, right? So that interval look like 1 second. I mean, when you say the observer at x2, of course, is seeing both the clocks, except that it's seeing this one a little late, right? It's whatever is emitted at x naught, it reaches at y naught.
So there is some notion in which there's one clock which is staying at x1 and another clock staying at x.
Yes.
But so basically you're saying there will be another observer watching this clock and they are at the same point in some space. So I'm asking if there's such a
They are at the same point. No, they are at different points in the space.
but they're at the same point in space.
Same point in time.
Staying at the same point in space.
Yeah, there are observers, of course, you can say. I mean, one event is x naught, x1, right? And then there's another space-time point x naught y, x2, right? But it's just that the light signal doesn't reach x2 at that time, right?
Are we initially considering that the absence of gravity when these two clocks are separated from x1 and x, are they simultaneous? Are they synchronized?
No, not necessarily, because you'll only relate delta x naught to delta y naught. Even in the absence of gravity, you don't need it, right? All that is needed is that they move at the same speed, so that because you'll be comparing delta x naught and delta y naught, right? You are not going to try to compare x naught and y naught, because that confusion is not there.
Synchronizing the initial position, but the speed which
Synchronizing meaning you have to be able to compare x naught and y naught, right? Because times, actual absolute times, but we don't care about that, right? That's why you only need the difference, right? Because you are trying to observe the difference between two arrivals of signals, right? The signal comes from the first movement, and next the signal comes from the second movement. in absence of gravity, well, we will not assume anything. We have to derive it, right? Even in presence of gravity, they will be the same, but you have to prove it.
This formulation, we are using one in both locations, one in.
Yes.
I mean, is it possible for us to use another coordinate? I mean, is that affect on that?
No, the final result cannot be affected by coordinate system, right?
Final result would mean the delta tau calculated at 1, delta tau 1, and the comparison between delta tau 1 and delta tau 2 won't change
No.
irrespective of what we use.
No, it will not. I mean, you can just, once you have done the calculation, you can change your coordinate system to anything, right? It will not change anything. But it's useful to, if the system is static, right, it's useful to use a coordinate system in which there is no explicit time dependence. Okay? Otherwise, the calculation will be much more complicated. Is this clear?
Here you mean it's very convenient because the signal that traveling from 1 to 2, the null geodesics, I mean for the first clock movement and the second, I mean yes, the second hand of the clock. I mean the first set of events and the second set of events in null geodesics
Will look similar. They are not exactly the same. We will see in what sense they are similar.
If we had some sort of a coordinate system in which mu was function of not just x vector but also x cube,
Then things will be more complicated, clearly. Yes. That here we will show that delta x naught and delta y naught are equal. That will not be the case if the system was time dependent. Okay. Now, intuitively, you can see why they should be similar, right? Imagine that you have static geometry, right? You go from one position to another position. It requires some time, right? So it starts with x naught and it is there at y naught. But because things are not changing as a function of time, right? If you if you emit a signal at say x naught plus delta x naught, right? As far as the space part is concerned, it is expected to follow exactly the same trajectory, right? Everything will be delayed by delta x naught, right? Same trajectory, but with x naught getting shifted. So if it starts at x naught plus delta x naught, it will reach at y naught plus delta x naught, right? Which means delta y naught should be equal to delta x naught. Okay? But let's try to make it formal, right? How to prove this formally, because it will be useful for manipulations of this kind. So the point is that if x mu equal to f mu of u is an null geodesic, then x equal to I'll f0 of u plus c and f of u is also a null geodesic for arbitrary c, arbitrary constant c. Okay. First, let's try to check that it remains null. Okay. So g mu nu dx mu du dx mu du g mu nu of x is null, right? So this means that g mu nu of x df mu du df mu du equal to 0. Yes, indeed. Okay, this statement is valid only for that case. So now we have to check if this also satisfies that, right? So to check this, what you have to do, you have to change x. Here it was f of u. Right, because x is f of u. So you see that because it depends only on the vector part of f, this remains the same for the new trajectory, new curve, right? These ones don't change because these are derivatives, right? Constant shift doesn't change the derivatives. So this is the important part because G mu nu depends only on the spatial coordinates, space coordinates. A shift in time, right, doesn't affect this. Similarly, the geodesy equation, let's look at this. Here again, gamma is argument. Gamma, of course, is made of derivatives of G, of metric, right? And the metric has this property that it only depends on the space coordinates. So argument of gamma remains f of u, right? Even when you change f of u to, even when you shift f naught, and these are all derivatives, right? So under the shift of c, it makes no difference. Right? So both equations, so both of these equations basically hold for any c if it holds for c equal to 0. Right? And we have assumed, of course, for c equal to 0, it does hold. Is that clear?
For our case, C will be delta x 0.
Yeah, so for our case, c will be delta x 0. Okay. So let's now see what it means, right? So the first trajectory, okay, so the first ray has the following property. So f 0 of u is x naught, f of u is x1, sorry, f of f0 of 0, u equal to 0. Is x1, f0 of u equal to 1 is y0, and f0, f of u equal to 1 is x2. Right? It starts at x1 at time x0 and reaches at x2 at time y0. Now you choose a new trajectory. Take a new trajectory. f0 of u plus delta x naught and f of u. Because I have basically taken c equal to delta x naught. I can take c to anything that I like, right? Let's take c equal to delta x naught, because the claim will be that this is the trajectory. This is of course a null geodesic, right? Because original was a null geodesic. Okay? And the claim will be that this is the one which describes the second ray. Okay? So let's check if it satisfies the correct initial conditions. Right? So f0 of 0 plus delta x naught is x naught plus delta x naught. Right? It starts at x naught plus delta x naught as 1. Okay. F of u equal to 0 is x1. It starts at x1 at x0 plus delta x0. which is okay. F0 at u equal to 1 plus delta x naught, right? We have shifted by delta x naught, so this is y0 plus delta x naught. We don't know if this is right or not, right? But first let's check where it reaches. So f of u equal to 1, okay, f is not shifted, so this is x2. Pardon? No, y0 not y0 plus delta x0 because I'm just trying to see. I'm not saying claiming to begin with that this one is the new trajectory we want, right? But I'm simply saying that let's suppose that there is an null geodesic which has the first ray. I'm now making this transformation of this kind. Okay, just shifting the argument of f0 by some constant, and that constant I have chosen to be delta x0, right? So wherever there is an f0, I have to replace by f0 plus delta x0, right? That's why you get delta x0, right? So what it's showing is that this null geodesic that we have found starts at x0 plus delta x0 at x1 and it reaches x2, right? Time we had no control, right? We calculated the time. So that must be delta y0. This by definition is y0 plus delta y0, right? So it's supposed to reach the point x2 at time y0 plus delta y0. So this then shows that y0 plus delta y0 is indeed x0, is y0 plus delta x0. So delta y0 is delta x0. Yeah, so the first one we have fixed completely, that's an null geodesic that starts from x1 at time x0 and it reaches x2 at time y0, right? Y0 in principle could be calculated if you knew the geometry, right? But we don't need to calculate it. Let's suppose that it's at y, because it's at y0. Now I am saying that let's forget about being able to reproduce the second ray. We'll come back to that later, right? Just construct a new null geodesic by this procedure, shifting by c, and I have chosen by c to be delta x0. Right? Then the new null geodesic will have the property that everywhere there is f will remain vector f will remain vector f, right? And wherever there is f0, I'll replace f0 by f0 plus delta x0, right? So that's I'm now calculating what is the initial point of the new null geodesic and what is the final point of the new null geodesic, right? What you find is that the initial space point and time points are what you want for the second ray. The final space point is what you want for the second ray, because it has reached x2, right? Final time point, we have no control. We have to get what you get, right? And that is this one. So this is a new null geodesic that starts at the right time at the right point and ends up at the right point, right? What time it ends at is not our control. That will be determined by the solving the full equation, right? But we are not solving the full equation, right? We are simply using the fact that this translation will automatically solve the equation. That's the argument, that if we could actually solve it, right, we could separately calculate what delta x0 is and what delta y0 is, and we could compare, right? But just by the fact that there is a symmetry under that given one null geodesic, you can generate one by time translation, right? Using that to show that if the next ray starts at x0 plus delta x0 at x1, it will reach x2 at y0 plus delta y x0. Well, I have just chosen C to be constant, but you are asking.
And you have shown that that's a solution.
Yes.
But now the problem is that if you have a solution, you have to show that it has to be a constant.
That it has to be, what has to be a constant?
Let's say C is a function of u.
Yes.
If it has to be a solution of this form, if the geodesic has to be of this form, given that f mu of u is a geodesic,
yes,
you have to show that C of u has to be a constant.
So you are asking whether there are more than one null geodesics. I found a null geodesic between right? You're asking whether there's more than one null geodesy, right? Typically, if the points are sufficiently close, right? Sometimes it may happen that if you have a very long winding route, you may find more than one null geodesy, right? That's where the gravitational lensing comes in. Okay? But as long as they're close enough, you can show there's a unique null geodesy. I mean, you know from everyday experience, right? That starting from here, right? If you send a light, if you want to send a light ray to the moon, I can decide when we start and at what position we start, right? And the final position I fixed, it's the moon. But you have to control on when it reaches moon, right?
Then it can happen, but if there's a sun in between, you can do this.
Yeah, so that's the gravitational lensing, right? If there is sun in between and if it has a very strong gravitational field, then it can go like this, right? We're assuming that there's nothing so strong in between, right? So there is more than one null geodesy, right? That basically says that when you see the clock is ambiguous, right? That you could see the clock this way, you will see at one time, and if you could see the clock that way, you will see at a different time. Okay? That could happen. In that case, you say that okay, you will only see the rays, you direct your eyes in one particular direction in space, right? So you only see the ray that is coming from that direction, right? So that you are sure that in the space, it's following the same trajectory.
Even there, with the gravitational example, it's still a simple example in which your view is such that v equal to 0 gives you c, u equal to 1. But I'm asking, will there be a function which gives you something else?
No, small changes, right? It will not work. Weak field, you can check that null geodesics are unique. See, this is the difference between null geodesics versus ordinary geodesic. Space-like, say time-like geodesic, right? Because time-like geodesic, right? You have a choice of when you want to reach the moon. Suppose you want to send a rocket from the Earth to the moon, right? Okay. Then suppose you don't want to reach too fast, right? You will just send the rocket slower. Right? The initial speed is up to you. Light has no such control, right? Speed of light is fixed. Right? So while you are right that if you have a strong gravitational field, you can do lensing, right? You can go in different directions and reach in different times. Right? But in weak gravitational field, you don't expect such things. Oh no, that's going in exactly where you said, right? That I have found one trajectory. That trajectory exists, right? I have not shown that no other trajectory exists, right? That's what the assumption of weak gravitational field is going. Which is also weak, exactly. Yeah. Yeah, you can say earliest time. That if you see the clock, the hand moving, second hand moving, right? If there are two different images you are seeing, right? One image moves a little before the other. You can always say that you will see the one which is moves fast, right? Or the direction. You can fix the direction in which you look, right? Because different null geodesics, if it exists, right, they will come from different sides. No, true. But what he is saying is that if you want to compare, right? If you want to make sure that you are looking at the null geodesic that follows this time transition, right? There may be other null geodesics. Okay. Imagine the first one you have seen. So this multiple image, then you will see both for the first tick and the second tick, right? So the first tick, you look at the one signal that arrives first, right? For the second tick, we also look at the signal that arrives first. Right? As long as that you make sure that you are looking at the same path, right, in space, you are done. Right? Because those are the time transitions of each other. The other parts may be more complicated parts. Is that clear? Okay, so you have got delta y naught. Now you have to convert it to proper time. So delta y naught, right? So this is the interval in x naught that the clock, the observer sees this difference. So in interval delta y naught, how much proper time will elapse in clock 2, clock at x2. This is a relevant question because observer at x2 is measuring the time with the clock at x2, right? So how much time it takes between two signals will be captured by how much proper time the clock at x2 measures, because the clock at x2 is by the same logic, okay, is ticking every 1 second in its proper time, right? So how many ticks in that in this process will be captured by the proper time that elapses in the clock at x2. Okay, so that is of course easy. So this is let me write delta tau square. So this is, we have calculated already the proper time. We have so delta x was, so let me, right. So this we have proved first that this is delta x naught square. Delta y not equal to delta x naught is what we established there. Okay. And now delta x naught we have calculated. Okay. So this is minus okay, I have just substituted a formula for delta x naught from that line. Okay, so delta tau at time delta tau in clock 2 will be square root g00 x2 over g00 x1 times 1 second. Because the clock at position 2 is not going to see 1 second in interval. Right? It will look like from position 2 that the clock at 1 is either running slower or faster, right? Depending on whether the ratio is larger than 1 or smaller than 1. Is this clear? So let me now describe the weak field approximation.
Last time we got something like the presence of a gravitational field, the component of the vector.
Yes, indeed. So G00 is related to the gravitational potential, right? That's what we had seen in last class. Yes, so let's work it out. So weak field, right? G00 we wrote as eta 00 plus H00, right? Eta 00 is -1 and H00 is minus 2V over C square, right? 2 minus or plus, I don't remember now. Is okay? Minus. So you will get delta tau in clock 2 is square root of 1 plus 2V of x2 by C square divided by 1 plus 2 V of x1 by C square. So this is roughly 1 minus, if you expand it out, V is small, right? That's the weak field approximation. So 1 plus V of x2 minus V of x1. Plus higher order terms. So the effect is small because there is a 1 over c square sitting there. Okay. So let's suppose that x1, x2, the observer, suppose that x2 is far away in space. And x1 is close to the surface of a heavy object. Okay, like a star or planet. Then V of x2, so V of x1 then is, sorry, V of x2 is almost 0 because far away the gravitational potential is 0. And V of x1 is negative. Right? Gravitational potential of a massive object is negative. Right? So, and the closer you are to the surface, the more negative it is. Right? Minus gm over r. Right? That's a formula that we are using. So you see that in that case, this ratio, this will be larger than 1. Because it's 1 minus a negative quantity, right? So this is larger than 1. Which means that a clock in space, right? An observer sitting in space will feel as if the clock on the surface of the planet or the star is running slower. Because it's taking longer time, right? It's longer than 1 second. Between 2 ticks, right? You are spending longer than 1 second because that observer in space only has the clock that he or she has, right? That runs delta tau is 1 second for every tick of that clock. Right? Whereas the clock which is on the surface of the planet or the star, okay, that signal, okay, 2 successive signals reach at larger interval than 1 second. Right? So the conclusion will be that the clock on the surface is running slower. And later on, when we study black holes, right, we will see that this ratio actually becomes infinite. Okay, if you place a clock at the horizon of a black hole, right, which is the closest you can get to, then this ratio becomes infinite. Right? So that's what is called the infinite redshift. Okay, this event is called, this phenomena is called the gravitational redshift. Okay, why redshift? Because the clock slows down, but that means everything slows down, right? If you look at the spectral line coming out of the an object placed on the surface of the star, right? The oscillations of the atoms and molecules also slow down. Right? So it looks like that the spectrum shifts towards red. Right? All frequencies, right, gets reduced, all wavelengths, okay, get stretched, and all frequencies get reduced by this factor. Okay. So it's a uniform redshift, right? The ratios remain unchanged, but everything gets redshifted. Just yeah, infinite redshift basically means that you will not see any light, because if the frequency get stretched, if the frequency becomes close to 0, right, then I mean in quantum theory that the energy carried by each photon, for example, right, is proportional to frequency, right? And if that goes to 0, then basically you don't see anything. No, not this formula, not this formula, but this formula is okay. Right? So this is the formula which will give you infinite that shift, right? Not that one. Okay, so finally I should say that this is looks like a mathematical result, but this actually has a practical application. Okay? Because this effect, without taking into account this effect, right, the GPS will not work. You know how GPS works? You see your position, right? What tells you what your position is? So basically, you measure distances, right, from some satellites which are moving around in the sky. Okay? And the positions of those satellites are known because they follow definite trajectory. Right? And if you can figure out your distance from those satellites, you know your position. Right? That's clear, right? If you know the distance from 3 different objects, right, that pinpoints your position. Now the question, how do we know the distance? That you are not going to measure the distance to a satellite, right? That's much harder than finding your position on Earth, right? So what you do is that the satellites are sending out signals at regular interval. Okay, and that's also programmed, when the satellite will send signal. Okay? Your phone, okay, is receiving those signals, but a little later, right? Because it takes time for the signal to propagate. Okay? And based on that, you know how much light travel, how much time the light took to travel, right? And that gives a distance. Right? That's how you calculate your distance. Okay? But this requires that your clock has to be synchronized with the satellite clock, right? Because satellite emits at regular interval, which is programmed, right? You're comparing that with the time that your clock is measuring, right? So your clock has to be synchronized with satellite's clock, right? Which you may do once, right? But then the satellite clock is moving fast, running faster than you, right? Because you're on the ground, right? You're closer to the Earth, so your clock will be slow compared to the clock of the satellite, and that effect has to be taken into account. Right? So when GPS works, right, the GPS has already this program, built-in program, right, which corrects for this fact that your clock is running slower than the satellite clock. Okay, so without general relativity, your GPS will not work. Right? So that's one application of general relativity. Right? Even though it looks like very abstract object, right? 1 over c square, how will you detect this? But it is important, right, in precision experiments. What?
That we use 3 satellites instead of 2.
They use 3 satellites, but I think that is probably not good enough. I'm not sure, because you have to synchronize your clock, right? Because it depends on how much time has elapsed, right? So I think you do need to synchronize your clock. I mean, so it's basically inbuilt. I mean, once you know the effect, then you can correct for it, right? You know how much slower your clock is running, right? So in the satellite, when you say the satellite ticks at a given time, right, that time in your, from the point of view of the observer on the Earth, right, is a little, I mean, if you are the satellite was, so the satellite, the intervals between 2 successive emission, right, is a little shorter than what we would think, right? So that has to be taken into account. No, it will not work, because then even the null geodesic, right, will change. Well, there is a similar formula, of course, right? Because once you know the principle, right, you have to basically calculate the. I mean, here we just related delta y naught to delta x naught, right? There you have to actually calculate delta y naught, right? If the space time is time dependent, but it's certainly possible to do this calculation, right? It's just that it will require more work. That you have to do that calculation. Exactly. Yeah. Okay, so I think I'll stop here.
Some theories are there which like where principle of equivalence is violated. So in those cases when we have like patches where laws are varying, like we have different laws and different sort of patches.
Not defined laws in different sort of patches. It's just that, sorry. It's just that you change the laws by adding some extra term. Right? Just like we did here. Exactly. Yeah. Yeah. Right? Here the point is that the physical force is removed completely in the local energy. Okay, gravity can be removed. Right? Here, even if you go to local energy, gravity cannot be. There is an extra effect because that depends on it.
Yeah, I didn't understand this. You're writing delta x0 equal to delta y. For example, if I am sending one light, right? Initially, first 1 second I send the light. And if I am emitting the next light, right, 1.5 seconds, by that the time at which I am emitting the second light, your time will be 1.5. And it will again reach like 1 second. It's again the same sequence.
Yes.
So you will detect the signal at 3.5. One, you first 1 second I emitted the first one, you received it at the second. And I'm emitting the next step there after 0.5 seconds. So it is like you will receive that 3.5 seconds. So this is not clear. Like how the delta x0 to delta y0 actually filters send the next pulse. That much is the only time that time can be. But actually there is a time that light will take to travel.
But that is the difference between x0 and y0. That you are not calculating. You are saying that suppose you send the signal at 1, I receive it at say 2.5 seconds. Then you send the signal at 2 seconds. I receive it at 3.5 seconds.
Right? That 1 second will be the
Exactly. So that's what you are calculating, right?
Yeah.
Because we are not trying to compare y0 with x. Okay. So that will require even synchronizing that.
And in this situation we have a static radiation.
Yeah, exactly. And if the gravitational field was not static, then this 1 second difference should not remain 1 second.
Okay.
Right? Because the change in gravitational field will in the you follow a different null.
Since there is a very static gravitational and it's weak, that's why this delta x0.
Okay, weakness is not part of this. Okay. This argument works even if it's not weak. So as long as it's static gravitational field, that basically means that you have constructed one null geodesic, and then if you take another curve where only the time gets shifted by constant and nothing else changes, that also is a null.
Yeah. I'm just trying to relate. Maybe I'm mixing up. But since there's a gravitational, as you said, there will be at position 1 and position 2, the moment of clock will be.
Yes.
So, but by writing delta x0 equal to delta y0, usually there is no.
Oh, because I'm assuming that the blocks are held in that position by some external force. Right? So that the block is going along the trajectory where only x0 is changing and x1 is remaining fixed. And the same is true for the observer. Right? So these are what you are saying is if they are going along the geodesic, right, then their positions will also change. But I'm not assuming that the initial and the final clocks are going along. They are just held in that position by some external force. It's like if you want to suppose you have a planet, right? And if you want to sit say 100 meters above the surface of the Earth, right? You have to run a rocket, right? Which balances the gravitational force. So assuming that has been done, right? So that you're not moving. And the same is true for the clock.
This can be confusion I have. But whenever we say something like, for example, here to Earth, with respect to the outside observer, the clock runs at Earth is for a 1 second in the phase shift. Then in that case, is it really like 1.25 seconds is something like a time getting slower for us, or it is running faster?
So normally you see that if you are observing something, right, where the intrinsic speed is you are observing that it moves in say 0.75 seconds, you say that your clock is slower than that one. Okay. Because by the time it has moved 1 second, you are not doing 0.75 seconds. You are observing say 1.25 seconds, then you say that that clock is running slower. The same interval in two clocks, right? If a 1 second interval in the first clock, right, is more than 1 second in the second clock, then the first clock is running slower. Okay. Because from the point of view of the second clock, you have spent 1.25 seconds for the power to run one.
So there is a similar kind of paradox becoming to observe this switch.
Here it's not a paradox, right? It's not like special relativity where there is a relative motion A is slower than B, but and B is slower than A. It's not like that. Right? Between these two observers, there is no confusion about which one is slower.
Yeah.
Because from the point of view of x1, right? I mean, that is said, if you have a point in space, right? Then from that observer's viewpoint, our clock is running slower. But from our viewpoint, that clock is running fast. Right? So this paradox involving relative motion is not.